like I said, this lesson is very brief. It's something that in years past, sometimes I don't even teach. It's something you can get by without, but it's an added little tool that you would put in your arsenal that's helpful in graphing functions sometimes. It's not always helpful. This is called the second derivative test. And to begin with here, the second derivative test, what we're learning today, is not about concavity. And this is not a typing mistake. I'm saying we're learning how the second derivative can tell us about max-mins, which is normally what you use the first derivative for. But the second derivative, there's a way to sneak in the back door here and get answers for max-mins with the second derivative. Not always. So as a background to what we're talking about here, to review some things about max-mins, all points where f prime of x equals 0 or is not defined are considered, I guess, potential points that could exist at those locations because there's a max or a min, right? So if you determine that the critical value of x is, for the first derivative, 1 and 4 and 7, then at 1 there might be a max or a min. At 4 there might be a max or a min, and at x equals 7 there might be a max or a min. There might not be any max mins on any of those points. They're potential max mins. Normally what you would do once you've identified those potential points where max mins might occur is you do a first derivative chart to determine which, if any, are maxes or mins. That's what you would normally do. But you don't need to always. There are certain functions where we can then use the second derivative to determine whether they are max-mins. Listen carefully. Where we use the second derivative to determine if the critical values of the first derivative are max-mins. And it would be very specific. If it determines that it's a max for sure. And it doesn't require a chart. So don't confuse this with what we just finished doing yesterday. That's called a concavity test, and it uses the second derivative. But it uses a second derivative chart. So this is why sometimes I don't teach it, but I think it's a valuable tool for other things, so I decided to teach it again. This doesn't work. The second derivative test to find max-mins doesn't work for all functions. Okay? So the question is, why would you use it then? Of what use is it? It's because for certain functions, specifically polynomial functions, and there are other ones as well, not only does it always work with polynomial functions, it's very quick. It's very simple and very quick. So that's better than some long, arduous task, right? What does the second derivative test say? Let's say that f prime of c is equal to 0. I guess what I'm telling you is c is a critical value for x for the first derivative, because f prime at that point is 0. If I say the second derivative at that critical value for the first derivative is positive, then there must be a minimum there. Why? Because the graph has to look like this. If the first derivative at c is 0, something going on out there I should know about? If the first derivative at c is 0, the slope of the tangent is 0. Would you agree the slope of that tangent at c would be 0? Well, why do I know that it must be a min? Because it's concave up at that point, because the second derivative is positive. I don't care how you cut it. This is a subset of everything we've learned. If it's concave up at a point where the slope is 0, it must be a minimum. Has to be. Similarly, so the first derivative is 0, the second derivative is positive because it's concave up. The first derivative is 0 because the slope of the tangent is 0. It's horizontal slope. Second derivative is positive because it's concave up. If f prime of c equals 0 and the second derivative is negative, there's only one way that can happen. If the second derivative is negative, it's concave down. It has to have that shape. And if the first derivative is 0 at c, then the tangent must be horizontal, so that must be a maximum. I mean, these two conditions here, without the graph, indicate that you're talking about a minimum value. It has to be. There's no other way you could conceivably come up with the function. Notice that this only works for max-mins where the first derivative is 0. If you were finding max-mins and you found the first derivative and you had a whole boatload of critical values and some of them were critical because the derivative's not defined, then this test is not for you. It's not to be used in that situation. And because polynomial functions just wobble up and down, not forever, sine functions do, cosine functions do, but since polynomial kind of wobble up and down until they take off in their respective directions, this is ideal for that. So let me show you how quickly we can find max-mins. Use the second derivative test to find all extrema of this cubic polynomial function. Well, we find the first derivative, which is 6x squared minus 6. And we're in grade 10 math right now looking at that thing. I can factor a 6 out. I wanted to just write 6 times x plus 1 times x minus 1, but we'll do it in stages. So the first derivative is this. Now, given that we're only doing this today with this stuff so that we can say what the critical values of x are, you don't even need to factor it. I mean, if you can see x equals plus or minus 1, that's good. We don't need it factored because we're not going to do a first derivative chart. What we are going to do is look at the second derivative. And I hope it makes sense that you're going to differentiate the first derivative from that point, not from some factored form. And the second derivative is 12x. So, if we make a table of values with the critical value of x for the first derivative and the second derivative, we can determine if they are max-mins. When I put negative 1 into 12x, I get a negative result. So think about what that means, because you're not always going to have this thing in front of you. Think about what that means. When x is negative 1, the slope is 0 because the derivative is 0. Right, these critical values of x make the derivative 0. So that means the slope of the tangent at negative 1 is horizontal. But it's concave down because the second derivative is negative. It has to be a maximum. At positive 1, when I put positive 1 into the second derivative, I get a positive result. Don't worry about what the value tells you, okay? You know, the value of the first derivative tells you the slope. Don't worry about what negative 12 tells you about the second derivative. It's the slope of the slope. It's a weird thing. But we get a positive result here, which means that at positive 1 we have a minimum because positive is concave up. And if it's concave up, it has a lowest point where the slope is 0. So what we've determined with the second derivative is there's a max. There is a max at negative 1 comma some number and a min at positive 1 comma some number. To find those numbers, we just find the y coordinates by looking at the x coordinate in the original function. So I put 1 in and negative 1 in. When I put negative 1 in, I get 17. Help me out here. Pretty sure I get 17. And when I put positive 1 in, I get 9. I admit there are some people, although I don't believe there are a lot of you based on watching you do the quiz, who would much rather do the chart. But I think this is simpler. One more example. So we find the first derivative simply, well, not simply, for two reasons. One, so we can identify the critical values of the first derivative. Two, so we could then find the second derivative. Well, why don't we find the second derivative right now? And there is absolutely zero reason to factor the second derivative. We don't care about any critical values of x there. We're not talking about concavity or inflection. Can you double check my first and second derivatives? Thank you. This first derivative, I really don't like writing equals equals, but I'm going to do it anyway here to save a bit of space. I can take an x squared out and be left with 8x minus 3. My critical values of x, and I'll be more specific here, for dy dx are 0 and 3/8. The value of the second derivative at those critical values of x for the first derivative will tell me which of them are max, which are min. And since it's a polynomial function, the function's defined everywhere, the derivatives are all defined everywhere, you're going to get an answer here. When I put 0 in, interesting. Interesting. When I put 0 into the second derivative, I get 0. We do get an answer. And I had to just think about what it is and what it's telling us. The answer is that at x equals 0, it's not a max nor a min. Okay? And the reason is going to be that there's a multiplicity here on the polynomial function. But I'll show you the graph in a second. When I put 3/8 in, we're putting it into the second derivative. I couldn't tell you. You're going to have to crunch those numbers for me. Can't do it. You're getting a positive result. I hope you get the same number I do. So what that tells us is that at 3/8 there's a minimum because a positive second derivative is concave up. And I always have to do this with the second derivative test. I'll be honest with you, I don't like the second derivative test. It's just too limited for me, that's all. But whenever I do it, I have to ask myself, what does this mean? And I have to visualize in my head this shape. And that means that there's a minimum. I'm tempted to say there's a maximum because plus tells me something is up, literally. But there's a min at 3/8, comma, and I don't want to spend time doing this. If you want to figure out what that y coordinate is by putting 3/8 in for x in the original function, you go right ahead. I think that at 0 there's an inflection point. So it's critical because the slope is 0. But if you did a first derivative chart, you would discover before x equals 0, the function is going up, and afterwards it's going up. That's what you would discover. And by the way, since you can factor an x cubed out of this, you should know there's a multiplicity of 3 based on Math 30 rules. So if I take a look at this function, this is not part of the question. I'm just I misspoke a little bit earlier where I said you're going to get an answer. It's either going to be max or a min. I didn't think that thought through. It's not always going to be a max or a min. It could be an inflection point, but let's take a look. See, and again, not to rationalize things afterwards, but this is one of the reasons I don't like it. It's not, there's exceptions to things, and it's not going to point out maxes if there's cusps or other weird features. I don't like having to have one special tool in my basement that sits there until it's ready to be used for one case. I would rather have a multi-tool. Well, I know I know it's going to be an inflection point there. There's an inflection point there, trust me on that. I know it based on that function, as long as I've entered it correctly, and I have. Let me show it to you. It is going to be subtle. And there's a minimum afterwards. So at 3/8 there's a minimum. You can see it's dipping down there. So it's inflecting, and it is not the inflection point, everybody, through the origin there, is not this kind of inflection point. It's this kind. Remember, I think we saw that yesterday with a vertical inflection point, that it looks like it's along the axis, but it isn't. We keep zooming in. So that's the second derivative test in a nutshell. And there are some problems for you to practice.